Okay, probably a good question to ask was, is this better or worse than for instance, last chapter? Um, that's kind of a relative term. I'll explain that in just a moment. Okay, I gotta. So, no, that's fine because I marked you absent. I gotta mark you present. Except now we've been placed into lost, back into found. Okay, so this is this type of content, we could say, is maybe where physics and chemistry overlap quite a bit. Because you could really say this is movement of molecules, which would be probably more associated with that of physics than what it would of chemistry, but yet it's still relevant for that content. There's a reason that there's a space after this. Go ahead and write it down if you choose to. There again, I'm not going to walk around here and make sure you need to be writing this down. We're all young adults in here. But one of the things, especially it pertains to this question, okay, is probably a lot tougher than this one, even though this one looks like it's perhaps difficult. But one of the things, we want you to observe something. What is the most common letter for a variable that you see up there? I'm sorry, not a variable, but a label. Sorry.
Or mole, sorry.
J or G.
I hear G, I hear K, I hear J, I hear. Okay. Well, there is 26 letters in the alphabet. I don't suppose there's 26 ways of looking through this. We are talking about proteins in biochemistry. There's only 19 or 20 different amino acids that makes many different proteins, so kind of different, or I should say similar to English language. But with this, the most common variable that you would see up, or excuse me, label would be this guy, probably. Okay, joules, because what we're talking about here is heat energy. Okay, so we measure heat in joules, which is a misconception because you would say we don't measure heat in joules, we measure heat in what? Yeah, so you put your two together, degrees Kelvin or degrees Fahrenheit or degrees Celsius. Okay, that is a temperature. That is not heat. Those two, that term kind of overlaps one another. Well, what's temperature? What is heat? Well, one of the aspects that I think I had noticed, as maybe it was yesterday as well, if we close the door here, this thermometer says 70.4 degrees Fahrenheit, okay? Which, as the hour had progressed yesterday, I thought it was getting quite warm in here. Would we agree with that analogy? Okay, I don't know if that's nervousness or what might have led to that, but regardless, we made it through. But that scenario probably does not make any sense. But one that possibly would, okay, and that is, now don't take this the wrong way, but how many of you want to go to Hawaii at some point? Because it was what we want to do. That's what we went on our honeymoon. And how many of you have actually been to Hawaii? Okay? And that's probably why I gravitate towards those shows, Hawaii Five-0 and Magnum PI, because they take place in Hawaii. Okay? So that's why I choose to watch those. But regardless, can you find snow in Hawaii?
It's more like ash.
Is there snow in Hawaii?
There can be. There can be technically, but it probably hasn't happened for a while.
There's snow in Hawaii. Sure there is. There was snow when we went, even in December. If you know anything about the climate, typically I would say on average the temperature is going to range anywhere between 70 and probably 85 degrees Fahrenheit. But it might be the humidity that probably remains pretty constant as well. But yes, you can find snow. You just have to higher altitudes. So when we make sense of that, we know if it's 70 degrees Fahrenheit, how in the world can there be snow? Because isn't that supposed to melt? Yeah, well, the altitude will be an extenuating circumstance in that. Okay? So even though the temperature says 70 degrees, there is still snow that exists in higher elevations, because common sense would say there should be no snow in Hawaii. Okay? But that is evidently not the case. You could even look at it in possibly today's terms as well. And it doesn't even have to get this warm. It is 18, 20 degrees Fahrenheit outside. What happens to possibly snow? Because what temperature should snow melt? 32. It's 18 degrees outside. How is that possible? If it's 18 degrees Fahrenheit outside, and you just correctly told me that snow should not melt until it's 32 degrees, how's that possible? That has a lot to do with it, okay? Because as the sun gets higher in the sky, okay, the rays are a little more direct, that's true, but especially if you are standing on the south side of a building and that sun is out, that building is going to absorb a lot of the sun's rays. So it's probably close to 40 degrees standing next to that building, yet out away from that building is probably still around that 18 degrees. So that's why you see on the west side of the pool here, yeah, there's a lot of snow here, but it's starting to move away from the building. But you also have the parking lot, okay? Why is the parking lot important when we're talking about melting snow? What's the color of the parking lot? The asphalt is black, so that is going to absorb a lot of heat energy to transfer into the air. Because heat is an average amount of kinetic energy. Because we know from physical science, how do we label energy? Joules. So that's why you see joules, 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 kilojoules, okay? It's a measurement for that of heat. It's temperature that is an average amount, or temperature is just a reading, where joules is a heat energy that is the average of everything put together. That's why you see snow in higher altitudes at 70 degrees Fahrenheit. That's why you see snow melting below the freezing point of water, okay? Because it is an average amount. Well, we don't look at things that way. We're just maybe more so cut and dry. Okay, it's got to be 32 degrees outside before snow is going to melt. But water is doesn't like to play by the rules, okay? Because for anyone who knows anything about the physical properties of water, when it freezes, it does something very uncharacteristic amongst other liquids. It will expand, okay? And in short, you don't need to draw this. In short, what that means is you have all of these water molecules, okay, that are bonded to there and to here and to there, okay? Another hydrogen here, okay? And then you're going to have another hydrogen there. It's just how that molecule interacts, especially this hydrogen bonding, because what happens is when it freezes, it starts to push outwards, and that's why we say that it expands when it freezes. It also takes a lot of energy to raise the temperature in water, okay? That's why you never want to go to your stove, put your pot on there to boil what seems like everyone's favorite meal is pasta. Well, maybe, I don't know. But you don't want to be having your pot there and stand there and look at it. Why not? What makes it go faster? See, you're not old enough to know this phrase. Like, we know different types of phrases or cliches. Like with frogs, they say, you know, look before you what? Look before you leap. That's a cliche. Okay. Another one would be, a watched pot will never what? A watched pot will never boil. Okay. So for anyone who's ever waited in line at even a car wash, okay, it's about that time of year. Typically, on average, every car wash might take, we'll say, 7 minutes. 7 minutes is not a very long time, is it? But if you are sitting there in line, you think, this is taking forever. Maybe, maybe not. But it's just perception, you could say. Okay? Because water just doesn't like to play by the rules because of that hydrogen bonding. And that's what this problem will deal with down here. Okay, the reason that there is a space in here, how much iron do you want to try to melt? Grams. 5. It's got to be bigger than 5. It's got to be bigger than 20. Sorry. No. I like over 100. We'll go 134. Okay. But with that, okay, what happens here is you're going to want to ask yourself, what is the question asking? So if it's saying how much heat is a type of energy, which means it's going to be labeled in what? It's got to be labeled in joules or kilojoules, okay? So we see one of those terms right here. If we can get kilojoules all by itself, we'll know that we have the correct answer that we need. The reason that we needed a bigger number than that is maybe we're melting down a sword or an ingot of iron to make a sword. Anybody possibly gonna go see Dungeons and Dragons? I'm kind of looking forward. I might go see that, even myself. Okay. Honor Among Thieves. So Christopher Pine's in. I like him. I don't know if that's the right role for him.
Yeah, he definitely fits that role.
Okay. So another aspect you have to ask yourself, is this a known or an unknown substance? Why? You're right. Because it says so. That's right. It's iron. Okay? So remember, if we're talking about heat, the end result has to be labeled in what or what? Joules or kilojoules. So we've got this kilojoule here, so we need to isolate that and make that all on its own. Okay? So since this is a known substance, every time you see something measured in grams, okay, what you're going to do is probably convert that to what that we've done all the way back since last August. Okay, so how are we going to do that with a gram then? Okay, 134 grams of iron.
Divided by, what is it, like 55 point something?
Okay, so how are we going to get this into moles?
Divided by 55.
Okay. The atomic mass for iron is 55.85. Okay, grams. Every time you hit 55.85, you have what? You have a mole of iron. Okay, well, we're getting closer because which one of these variables have we crossed out? We've gotten rid of our moles. Okay, you just don't realize you have yet.
Oh, so then wait,
Okay.
you have moles on the bottom right.
Then what we can do is with this known value, which one of the things we're going to teach you how to calculate this, because I think it's going to be a vital tool. For those of you who go on in college, you're not always going to be given a substance measured in joules per gram degrees Celsius. It might be given to you in kilojoules per mole. And it's important to be able to know how to translate that between one and the other. So this comes from a table from a different author, So this value of 13.81 comes off of this table. Okay, so 13.81 would go up here. And what's our label for this? It would be kilojoules for every what? For every mole. Okay? So, what happens to these 2 moles now? What are we left with? Right. But I mean, when I say what's left, variable, sorry. Kilojoules, and that is an accepted value for heat. So then we've got our kilojoules just like what we needed. So can you use a different type of formula? Probably not for these, but you can for this one, and that's what all these variables are for over here, and I'll explain that in just a moment. So once you take 134 times I don't want that calculator. Well, I could use that one, but this was the one I was looking for because this one has all the answers in it. Okay. 134 times 13.81, and then divide that by 55.85, which would give us 33.13 kilojoules. Now, one of the aspects to think about is whether it is a type of metal. We got to wait till probably sometime in late April, probably May. If that sun is shining down with its direct rays onto the outside or exterior of your car, do you want to put your hand on the hood of that car? You're shaking your head no. Why would no probably be the correct way of looking at it? It's going to be a little hot. Okay? Now, you got to think about, okay, a hot vehicle. Okay, what do we say about this on your stove? Don't watch it. It takes a lot of energy to raise the temperature of water. Again, just because of its hydrogen bonding. Because when we look at specific heats, we can change these back to kilojoules per mole. We'll do that at a later time. Okay, so this bottom problem I want to go over, and then that'll be it for today. New material. Are we okay with this so far? Okay. So, rut row. Second row. Third row. Doing our head banging back there. Okay. And then it's okay to lean up against that wall, but when we're doing that, it looks like we're shaking our head no, but I know what you mean. Okay. So I'm just going to hit pause for just a moment, and I'll come back and finish this. Okay. Think about when this country was possibly founded, okay? Way back in the 1700s, okay? If you were going onto the frontier, okay, you probably had to hunt and take out and go hunting to feed yourself and your family. The problem with that is, does some of that go to waste? You're nodding your head, yes, that would be correct. Why is that though? Because what is different about the 1700s and processing a deer as opposed to today? In today's standards, when we process a deer, what would possibly be the difference? Once you're done processing it, where's it going to go?
Nowadays or back then?
Say that again.
Now or back then?
Now. Freezers were pretty hard to come by back in the 1700s. Because typically what would happen is if you didn't consume, I don't know if making jerky was pretty common back then. I would think so. Because once you've done that, well, you probably have a greater chance of extending the quality of your kill to feed your family. But nonetheless, you had to keep that cold. Why is that? So yeah, so it doesn't go rotten and go bad. So then at about the time of the late 1800s, okay, if you wanted to keep things cold, what did you have to have, do you think? Okay, ice, and then put it in a house, hence the terms ice house, okay? So one of the things that would happen is, even in today's standards, if you take a block of ice and just set it outside, it takes a long time for that block of ice to melt, just because it takes so much energy. But you go put your hand on the hood of a car, you're going to burn your hand. And that car is a heck of a lot bigger than that block of ice. Why is that? Well, what do metals do very efficiently? Conduct two things: heat and electricity. And that's why they get hot so quickly, because it conducts that so quickly. This either helps people a lot, or they're going to look at this and go, huh? So I don't know what side of the fence you're going to be on, because we want to try to do our best to explain what's happening here. Now, if you don't draw this chart, don't get bent out of shape. Oh my gosh, he put this up on the board and I didn't draw it. Don't get too bent out of shape about that. The difference between the question you had before and the question with what we see here, it should say change water. But what's happening to this water when you see this term and this term? Yeah, it's going from one state to the next. That's not really what you're doing with that iron. Yeah, it was going from a solid and just starting to liquefy, because it's not asking what its melting point was. You're just raising it far enough that it starts to melt. Okay, so we want to change water from ice to steam, which again, what is going to be in between the ice and steam? What phase? Ice is what type of phase, do you think? Solid. Water is a liquid, and then steam would be a gas, okay? One of the things, I know we're hitting 22 minutes. I'm trying to go as fast as we can here, but yet still try to retain this content. Do any of you have parents with coffee makers by chance, or even if you have you're boiling your water, and if you have a lid on that, okay? One of the things that's a really neat invention is, if we do this when we boil water for potatoes or pasta or whatever, if you have, it's actually a Pampered Chef product, okay? So it has a lot of little, what looks like doors on there, and it lets the steam through, because if you put a solid lid on that pot, eventually that's going to start to boil over, and then what does the water do outside of here? It goes over the side and all over the stove, and it makes a huge mess. But think about this. If you're not careful, when you pull that lid off, oh my gosh, that's steam. Steam is not 212 degrees Fahrenheit. It's actually a lot higher than that. So you have a greater chance of burning yourself. You might think, well, it's just boiling water. No, it's not boiling water. It is water in its gaseous state, because boiling is still water in its liquid state. Steam is water in its gaseous state, and that's why it burns so much easier with steam than it does with that of boiling water. So what we see happening here, how much ice do we have in grams? We want a bigger number than 100. Okay? Okay. So what we need to do is we need to raise the temperature up to where it's going to start to melt. So I need a temperature range below 0. Negative 13, you said? Negative 13 degrees centigrade. And we want to get this to steam, so it has to be over 100. 112. So negative 13 to 112 degrees centigrade. Okay? So what we're doing is we are raising the temperature of that ice until this starts to melt. Okay? So, again, what is heat measured in? Don't say degrees Celsius. That's temperature. Joules or kilojoules. Okay? So in this case, we've got 3 formulas we're going to deal with. A quantity of heat equals the mass times the specific heat times the change in temperature. Okay? That's one formula. Also, a quantity of heat equals the mass times the heat of fusion. And the third one, quantity of heat equals the mass times the heat of vaporization. Okay? This is a 5-step problem. But notice we only have 3 equations. So what that would tell you is that one of them repeats themselves. So that happens with this one. So steps 1, 3, and 5, we use this formula. This one is step 2. This one is step 4. Okay. So what we see happening here, we're starting at negative 13 all the way down here. So we want to raise that temperature all the way until that starts to melt. So this theoretically will start melting at this point, which is what temperature? 0. See, that's a common mistake. No one wants to put 0 in that because we think, gosh, if we multiply by 0, we're going to get 0 back. But that's why it's a trick question. I didn't know if anyone was going to get that right. If I was in your shoes, I wouldn't be smart enough to answer that back then. Of course, we're going back into the 1990s, which great time to grow up, the 80s and 90s.
Yeah, you love 2000.
It's okay. Yeah, it's still all a blur. I don't know. That's what happens when you get older. Okay, so at this temperature, it's 0 degrees. So if this is 0, where did this start from? Negative 13. So it's going to take a certain amount of energy to raise that temperature from negative 13 up to 0. Okay. Since this is labeled in grams, what variable must that be? Okay, so that is a mass. So a quantity of heat, that's what we want to measure because it's going to be in joules. This quantity will be its mass, which we know is 200. Is it 200? Yes, 200. Okay. So then the specific heat, where do we see this variable in this mess over here? Well, these top 3. Okay. And we put these in order. This is the specific heat for ice. This is the specific heat for water, and that's the specific heat for steam. Okay? So, our specific heat for water in its solid state, which is ice, would be what value? 2.06. 2.06. See, now you can say it correctly. Okay? Okay? Now, this logic, okay, you remember this good stuff. What did the F and the I mean? Close. Final. Okay? So, and of course that was over time. We apply that same logic here where that triangle T is just saying temperature final minus temperature initial. So you've done things like this before, but it was never applied in a temperature. Okay? So, our temperature range, where did it end? Where did it end? Where did it end? At 0. Okay? So we can put 0 in for this. Okay? Minus, where did it begin? Okay? And if we know anything about our algebraic skills, when you see two negatives like that, what do? Switch the signs and add. So that's how you get a positive value out of that. So that will give you a specific variable. Now, once you get to this point, notice you are not increasing in temperature anymore. Okay? Because all that's going to happen is you're applying just enough energy that that block of ice is just going to continually melt and melt and melt unless it starts to cool off again. But that's not what we're saying here. So again, this is step 1. So now we need to melt it. So from here to here, okay, is going to be step 2. So what does it tell us to do in step 2? Mass times heat of fusion. Okay? So the heat of fusion would be this variable right here. Because remember, it takes a lot of energy to melt water because, again, of that hydrogen bonding. So we've got our quantity of heat. I can just put it over here. Equals our mass, which was 200, times what? What does it tell you over there? 334. Okay? I'll show you just the 2 examples, then we can see, oh, now it makes sense. Okay. So now that we begin to melt that, now we're going to go through a different phase. So after you get it past 0, it's going to keep inclining until we hit this point, which is what happens there?
Boil.
Yeah, it's going to start to boil. So in step 3 now, which means we're going back to that formula. Okay? So in step 3, I got too many markers. Well, there's only 2. I keep getting them mixed up. Okay? So what are we going to put in here? Q, what's our mass? 200. Okay? Now, what is our specific heat for water? Okay? 4.184. And then, just like we had a temperature range down here, we've got a temperature range here as well. Where does water start to melt? Or excuse me, where does ice start to melt? 0. Where does water start to boil? So what would our temperature range be from here to here? Yeah, approximately 100. Okay? Now, there's going to be other extenuating circumstances, elevation, gas or atmospheric pressure, that could just switch that just a very little bit. But that is step 3. Okay? Now we're beginning to boil this water. Okay, just like we did here in step 2. Okay, so now in step 4, what is our formula going to be? Q again equals mass, which was 200 times, now we're starting to vaporize it, which means it's changing states from water to liquid, or excuse me, water to steam. And what is water's heat of vaporization? Oh, I was looking at this because 2,260. Okay? Then we have one more temperature change. Because this is still at 100, where did this finally come to an end at? 112. Which will be important here in just a that's not quite right. That's what I meant to do. Okay? So for our fifth and final step, okay, I'll put them up here. The mass has not changed. Q equals 200. What is steam's specific heat, which is this variable? 2.02. And then what was your temperature range? Remember, temperature final, 112. So temperature final, so when you subtract those two, your temperature range is just what? 12 degrees. Okay? Now, when you're dealing with all these labels, we said we'd make sense of that at the end, and that's what we're going to do. Because what we see happening is, notice that this is measured in grams. So a heat of fusion is measured in joules per gram. So what we see happening then, once you multiply those two, what happens to these 2 grams here? They cancel out. You're just left with joules. And joules is a way of measuring what? Measuring heat. Okay? Now, you might say, but these are on the bottom of one another. But it's still an inverse of each other because grams over 1, joules over gram, right? So that's how and why those cancel each other out. Okay? Then in one of these larger and longer step problems, okay, we still have grams. This variable is joules per gram degrees Celsius. And then this one is just degrees Celsius. So then you could use your same logic and say this is G over 1. This is degrees centigrade over 1. What happens to your grams just like up here? What happens to your degrees Celsius? What are you left with? And joules is a measurement for what? For heat. Okay? So once you find 1, 2, 3, 4, and 5, the quantities, you add them all together. Okay? So we will make sense of that tomorrow because we're already up to 38 minutes. I think that's enough because at this point you might not know what to ask. So other than the question you asked, just after 1 day, is this better or worse than gas stoichiometry? Oh, okay. Worse. That's because you just possibly don't know what to ask. So we will catch up to you next time.